in 6.2, we're going to look at some power series solutions of second order differential equations. So first we need to know when we can find a solution. Okay, first we need to know when we can actually find a power series solution. So for this section, there's actually two answers to that, and 6.2 and 6.2 deals with power series solutions around ordinary points, and in 6.3, the next section, Frobenius, deals with power series solutions around singular points. So they both have different processes, and before we actually do an example in this section, I do need to define some of these things. So if x naught is an ordinary point, then a solution to this second order differential equation can be written as a power series in the following form, where x naught is the center of the series, which we talked about in the last section. And since this is a second order differential equation, there will be two solutions. So there will be two power series solutions. It will be actually gotten from only one power series that we create. And what we'll see is there will be two constants, which will separate, and they'll form the two power series. And the radius of convergence of the series is at least as large as the distance from x naught to the closest singular points. So another word I want to highlight that we do need to define is singular point. And again, we also need to talk about ordinary points. So we're going to do this by also looking at some examples. So here's just a linear second order differential equation. So to match the differential equation up here, we need a leading coefficient of 1. So we divide through by a2x. And we don't need to write ratios or anything right now, because pretty much we just rewrite this by dividing by the leading coefficient, a2 of x, in every term, which can't equal to 0, so we can do that. And we get, and a1 divided by a2, we just call p y prime. And if you want, we can call it, we can see that it is a function of x. And q of x. So x, which is equal to x naught. So again, we can only build the power series in this section about x naught, we see here, if x naught is an ordinary point. So x naught is an ordinary point provided the functions p of x and q of x are analytic at that point, at the ordinary point. So what does analytic mean? Pretty much means p and q can be represented by a power series centered at 0. So you've all heard the term analytic, and you can think of it kind of like algebraic. But one of the an example of where a function can be represented by a power series is one we did in the last section. Was an example: e to the x was represented by x to the k all over k factorial, k equals 0 to infinity. So e of x is clearly represented by a power series centered at 0. That's centered at 0. So that's my x naught. And so that function is analytic at 0. So that would be my ordinary point. Just to give you an idea, if a function's not analytic, like in calculus 2, we use the Simpson's rule. There's more like a numerical process that we had to use because we couldn't integrate. So what I'm just going to do is just a lot of examples here of showing what singular points are and ordinary points, which will hopefully help you understand the difference. So ordinary points are used with the process I'm going to show you in this section. And if it's a singular point, then you build a power series around the singular point using Frobenius, which is the next section, the next video. So this second order differential equation, our p of x is equal to 3 and our q of x is equal to 5. These are constants. And so this function has no singular points. So if you remember from in an earlier section, I did kind of make the reference non-singular was non-zero, singular is 0. That's my little mnemonic device. So, so singular will be values that make the function p of x 0 in the denominator, where it's not defined. Okay, they're problem points. Okay, they are problem points because this is in the denominator. So there's obviously no problem points in p of x or q of x. You can think of singular 0 if it started off here. There are points in your, and I say there, but I do mean in a2 of x. Because when you divide through by a2 of x, then you've got your zeros in the denominator. So, but we've got to look at, that's just one case where we can come up with a singular point. So a1x, just a1x by itself, could have some problem points there that are undefined. That could be singular. So just to show you our next example. So here my p of x is natural log of x, and q of x is equal to x squared. So there's no problems in q of x. There's no singular points here. But here, at x equals 0, the natural log of 0 is undefined. So x equals 0 is a singular point. Going on to another example, the third example. So in this form, there's no problems. There's nothing that makes the denominator undefined, but we do realize, though, that this is not the right form. So I divide each term. Whoops. This is y prime. I forgot my y prime. So I divide each term, each side, actually, of the equation by x, And I get the cleaned up equation. So here, right here we have a problem. X cannot equal to 0. So therefore, it's singular at 0. So to clarify, we can see it can happen with P or Q. It doesn't matter which, if at least one P or Q fails to be analytic. I should say at a specific point at x naught is a singular point. And clearly, so we also have a singular point when the leading coefficient is 0 at x naught. That's also defined to be singular. So hopefully that explains the difference between ordinary and singular. So now what I'd like to talk about, or just give an example, is the radius of convergence. So to explain it again, the radius of convergence is the distance between the center, which is our ordinary point, and basically the radius of convergence is as far as that function is defined. Well, it's only going to be defined up until when it's undefined. So the distance will be between the center, which is your ordinary point, and the distance to the closest singular point. So that's our radius of convergence. You hit that point and it's undefined, and it can't be represented by a power series. That's not undefined. So here's our example. So we need it to be in our standard form with the leading coefficient of y double prime to be 1. So our singular points are when the denominator there is equal to 0. So let's solve that. I can pretty much see it's not going to factor. So I'm going to use the quadratic formula. So 4 minus 8 is minus 4, so that's 2i. So we have actually 2 singular points. So we have 2 singular points, and what we want to do to find how to build a power series for this solution, is we want to use the easiest center that we can possibly use. I would say the easiest center to build is when that x naught is 0, okay? And since 0 is not a singular point, that's what we're going to use. And I'm going to say use it whenever possible. And when is it possible? It's possible when that point is ordinary, not singular. So our distance, I want to draw what's going on here. So we're going to use 0, which is my ordinary. And I need to find the distance, which is our radius of convergence of the power series that we're going to find, that we could find. So it's going to be the same distance between either of these singular points. So I just need to find the radius between any of two. I'll choose the 1 plus I in the quadrant 1. It'll be easier. So you can pretty much see this is 1 to the right, 1 up, because of how to graph 1 plus I. So this makes a right triangle. So my r squared is going to be 1 squared plus 1 squared. R squared is equal to 2, or r is equal to square root of 2. So our power series, our solution is y equals the power series of a to the n, x to the n, is our solution power series, which of course we haven't found. We're not going to find on this problem. At least not yet. And will converge at least when x is less than 2. Want an easier example to solve than the previous one. So we're going to solve. So here, there's no singular points. There's no points where it's undefined. I can choose any point. Since all the points are ordinary, I can center it around any point that I want. So of course I'm going to choose my center to be around 0. Again, anytime 0 is not a singular point, we're going to choose it to be our ordinary point. It's the easiest series to come up with. So remember, what we have to do is we have to guess at our solution. So our guess is going to be just a power series. Like I said, we're going to have a solution power series. So my guess at a solution is y equals the power series Cn x to the n. N equals 0 to infinity. And just so you know, I really do have a choice. I could have used a to the k, x to the k equals 0. So the choice between n and k, it doesn't matter. We'll be flip-flopping between the two variables sometimes. And then also a to the n, c to the n, b to the n. It doesn't matter for that either, okay? I'm choosing c of n for a reason, because you'll see how we split up find our two power series solutions. We're not going to guess a second solution for this centered around an ordinary point. We might be doing that for Frobenius in the next section when it's centered around a singular point, but not around an ordinary point. It actually always just works out. So if this is my guess, I'm going to be plugging my solution in to my equation, just like I always do on my guesses. But we also need to plug in our second derivative of our guess. So we need to find the first derivative and second derivative. So I take the derivative, and we did this on the last video. And we just do the power rule. It will be n, c to the n, x to the n minus 1 to infinity. But remember, when we go in here, we plug in n equals 0. If we started at 0, we'll have 0 to minus 1, and it won't be a power series, okay? We can't have negative exponents. All over, it has to be a polynomial. So we do add 1 to this, so n equals 1. We'll bring this power to 1 minus 1, which is 0, which is the constant where I want it to start at. Now, the second derivative, same thing. But here, again, we have to start it at n equals 2 so that we have our first term being our constant. So now I have to plug this into my differential equation. So I only have 2 of them to plug in. This goes into there, and this goes into there. So let's do that. And again, just to copy my DE, so I can scroll down a little bit. So y prime goes first, and then my y term, which is this, which I'm plugging in. the series. And that's equal to 0. So just like we did in our last video too, we have to be able to combine these. We want to combine. So the first thing we're going to check is my terms. Check my first terms, my powers, basically. So check the powers of the first term. If those match, then all the other terms will match. So that's why we only have to check the first one. So I'm plugging in here, I'm plugging in n equals 2 into here. So I get n equals 2 minus 2, which is x to the 0. So that's my left side. So on the second one, we actually have two x's to worry about. We can bring this x inside, okay? But for now, before I'll check it, when I bring it inside, it'll be x squared times, when I plug in n equals 0, x to the 0, which is x to the 0 is just 1, so this is x squared. So these are not the same power for the first term. And so one way to make these match is, since we take the smaller one, and basically since the degree is 2 away, I can take out the first two terms. If I take out x equals 0 and x equals 1, then I can start my power series back up at x equals 2, which will make that x squared, which will make both sides equal. At the same time, I have to bring that x squared inside and combine those x bases. So over here on the first one, I'm going to pull out n equals 2. That's my first term. And so I'm plugging in n equals 2 everywhere. Okay? So that's 2 times 2 minus 1 times c2 times x to the 0, which will go away. Plus my next one will be n equals 3, which is 3 times 3 minus 1, c3, x to 3 minus 2, plus n equals 4, but I'm going to continue the series and just write exactly what we see here. And then this piece here, I'm going to rewrite, bring the x squares in, cn x to the, you add the exponents, n plus 2, and that's equal to 0 on the right-hand side. So just a quick check. When I plug in n equals 4 here, it's x to the 4 minus 2, which is x squared. And then here, we'll plug in n, whoops, I forgot to write it. So that's plus x to the squared. So they are both the same term. Now we can combine them. We have a little bit of busy work to do though, because we do want these to start at the same place, okay? I personally think k equals 0 is a good place to make them. Let me clean this up a little bit, just a tiny bit. We don't have to clean it up every time. And we'll find out soon enough that we don't want to write this, and we'll just want to do the math in our head. So this is 2 times 1, c2. The x to 0 is gone. This is 3 times 2 plus 6c3 times x plus, I'm going to pull this down a little bit. So again, that's always going to be the order. We want to make sure the powers match up. Now that we know that both the powers are x squared, we can do, we can set up the indices to be the same. So I'm going to just go with calling this k. And so my substitution, well, let me call this k, it's the same thing. So my substitution is k equals n plus 2. So k equals n plus 2. I like to write both equations, rearrange it so that I don't make a mistake when I'm plugging in, because we need both equations. So if k equals n plus 2, I subtract 2, n equals k minus 2. I'm going to use for this in a summation. And here, I want this to be k also, but we can see it's a different substitution. Here, n will be k plus 2, okay? So that's the substitution for the first summation. We want to substitute here, and n is 4, so if I put 4 in here, it's 4 minus 2, k is 2. And then the second equation, n is k plus 2. So n equals 0, n equals 0 plus 2, k will equal to 2. Notice how it's the same thing, and that's what we wanted. So it's c instead of n. Here n is k minus 2, x to the k equals 0, the same 0, and we have these two terms in the front. So now we're ready to add. So let's add these two series. So we do see we have this in common, but that's about it. We're going to factor that out. And inside, we're going to add this plus that and factor the x to the k. So now it's time for us to equate coefficients. It's very similar what we did to undetermined coefficients in trying to figure out the constants. If you don't see, every term on the right, every term, it's 0 plus 0x plus, let me expand that a little bit more. So on the right, it's 0, which is 0 plus 0x plus 0x squared plus, so every term of the polynomial is 0. That's what 0 means, okay? So this means this constant is 0. So I can set 2c2 is equal to 0. It also means that the next constant, the coefficient in front of the x term on the right is 0. And here's my x term here. So my coefficient, I do see, good thing I caught that sooner. That's a 6, I just copied it wrong. So my constant is 0. My term in front of the x term is also 0. And what this means basically is divide by 2, you get 0, c2 equals 0, and c3 equals 0. That's from equating coefficients. So now, these are all the other terms. Starting at x2, x squared, and x3, x to the third, and so forth. And we can see all the terms are 0. So we're going to set that equal to 0 also. Again, we can ignore the x to the k because we're just talking about the coefficient in front, and the coefficient in front of any x is 0. So we have also, I'm going to box that, and this is where we're going to get our recursive equation to figure out all the constants. So I'm going to try to solve for the bigger one in terms of the smaller one, because we have some of the smaller ones and we'll be able to work our way up. And clearly I want to divide by what's in front. And I do want to bring this out here to the right so that we can just have a coefficient in front of this. Now, you can keep it like this, but I kind of like my CKs matching up with my CIs. So I want to be able to have this CK. Obviously I can't keep it K. So I'm going to kind of do the same change of variable as I did with the series. I want CN. I want a definition for CN. Again, this step here is not mandatory. I think it's easier for the bookkeeping, okay? So clearly my substitution is K plus 2 is equal to N. And so I'll change everything in terms of N. So I can see here, this K plus 2, this K plus 2 is N. And then that'll be N minus 1. So for C of K minus 2, we also need to change K, which is N minus 2. So it's N minus 2 minus 2, which is N minus 4. So this is my recurrence relation. And I can start, well, if we look here, we've already found 2 of them, okay, which is these 2. So we have C2 equals 0 and C3 equals 0. Maybe the next one is C4. You can try C1, but we can see it's 1 over 1 times 0, which is undefined. And C2 is that one, and C0 is 1 over 0.2, which is undefined. So we didn't really have to find those. C4, now we can use this formula right here, recurrence relation, is minus 1. Since we can't really put C0 and C1 in the equation, we could choose C0 and C1 to be our arbitrary constants for the general solution. We'll see that later. So C4, again, don't be too quick to multiply out these numbers because we got to find a pattern. Once you know there's not a pattern, then you can multiply them out. So I don't see a pattern, so I'm going to go ahead and just multiply this. So that was C4, which is times C0. And so that's positive. And then 8 times 7 times 4 times 3, just punch it into the calculator. 56 times 12. So we can start seeing a pattern here, but then we have to go up and replace C5 with that. So in general, remember our solution. I always suggest to do this step so that you don't get confused. We start out with what the original solution was said to be. This was our guess. That's our solution, okay? So our solution was the power series, Cn x n equals 0 to infinity. So let's write this out. Plugging in n equals 0, it's C0x0 plus C0x1. C1x1 plus C2x2 plus, don't just write dot, dot, dot now. We know it goes on forever. But we have this to C9. Write them all out so that we have something to replace it. And then I'll say dot, 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 because I haven't written that more than C to the 9. Now, the reason why I like to do this first is some of these 0, C2 and C3. C2 is 0, C3 is 0, and look at this. They came back to, you get two things, and C6 is 0, C7 is 0. And so what we have left is the same y. Y is equal to C naught C1 x1. I don't need the 1 here. It's power. Plus C4 x4 plus C5 x5. You see what I'm writing? And then I have to say dot, dot, dot. Dot, dot, dot. Now, what I want us to notice now is there's only two variables. It came with the reiteration. There's only two variables. Before I do that, let's not forget to put the plus in between these. So I'm going to highlight all the C naught. C naught. Oops, I'm not done. So now what we want to do is use our substitutions from up here. Again, and finish it off. C naught plus C1x. It's not up there, right? Those are actually our arbitrary constants. Now C4, just C4 that I found. This is C4. And I write that. I replace C4 with minus, I guess I should write that as minus 1/12 C naught is my C4. That's a minus. And then times my x to the 4th. That's just C4. The C5, that's minus 1/20 C1. That's my C5. Plus CA is right here. And then the C9. I'm going to shrink this a little bit because I do want it to fit on one row. Not that it really matters. And it goes so on and so on. So now I want you to notice they're alternating with C naughts and C1s. So this is the solution. This is the general solution. But remember, we need two series solutions. Before I actually write out, before I actually rearrange this, I want us to recall that my general solution, remember this is homogeneous, right? This is homogeneous. Where did it go? It's homogeneous. And then my solution to a homogeneous, we get two solutions, y1, y2, right? And basically, it's y equals c1, y1 plus c2, y2. Or in our case below, doesn't matter what those arbitrary constants are, y, my general solution is c naught y1 plus c1 y2. This is what I'm looking at. And those are my two series solutions, y1 and y2. Okay, so let's write that underneath here. So our general solution is y equals c naught y1 plus c2 y2, and we have my two fundamental sets, or my two solutions, y1, y2. Okay? So if I rearrange these, let's go ahead and do that. I've got y. I'm going to gather up all the c naughts and factor that out. So here, here, and here. And then it goes on forever. It's 1 times c naught. Factor that out. And that'll go on forever because it's a power series. And then I factor out the green one, the C1. Okay, so what I have here is my Y1. What I have here is my Y2, here and here. When you add your two independent solutions, you have your general solution. So this is our general solution. So we can see here, if we wanted to, we can get rid of the C's. We can, we can choose, or, you're choosing C naught equals, I don't need to say that. So we can see here, thus, our Y1 is this series. And my second solution power series I forgot, I wrote here C1, but I'm supposed to write x to the 9th. Back out the C1. And that's also x to the 4th. Factor out the C naught, and it's x to the 4th. They're both infinite series. And that's pretty much how you do it.